Good afternoon, evening. This is October the 14th. We're approaching the midpoint already in October. I'm looking forward to the rest of the semester. I'm not going to rush anything. Everything's one day at a time. Just do what you can do. I'm going to lecture for almost an hour, I think, because I looked at the clock. I don't want to give you an infinite amount of time or too much time to be bored, but if I stop, by quarter till, you can have till 6 o'clock, and then 6 o'clock to 7:20 is more than 75 minutes, right? That's the standard period, so that's kind of what I'm thinking about. What I'd like to do is just say, are there any questions in thinking about the exam? Because I've definitely had a few in the last few days.
On the exam 2024,
okay.
I just wanted to make sure I wasn't seeing something wrong.
Okay.
The first problem.
Let me get back, open back up again.
First problem, when you plot it, at -1 you have 1/2, and should that be 1, or is there a reason that is 1/2?
Let me just look at this. 2 to the -1 minus n for n greater than or equal to -1. And then I think I tried to simplify it, but maybe I didn't do it right. So I put this 2 down below, so that I should have, so 2 to the -1 minus n should become 1/2 to the 1 plus n, right? Is that?
So I guess the question is, when you're plotting it,
oh.
n equals -1.
Okay.
Should that be 1/2 or should that be 0? And if it is 1/2, why?
It definitely has a term at n is equal to -1, so it should be, let's see, n is equal to -1. Yeah, which would be 1. So, okay. I see what you're after now.
Okay.
Yeah.
So it's not for some weird reason.
So this should be 1.
Okay.
Right?
Yeah.
Yeah. If I made that mistake and I didn't notice it when I graded, I can't remember. It's been a while ago. Well, last year, I guess. I don't know. I still have the old exams. I guess I can look at them. They're in my folder. I mean, in the cloud where I grade papers. But any other questions? The reality is, I make careless errors. You guys make careless errors. We hopefully resolve things, but we,
Yeah, I wasn't sure if there was some reason.
No, I'm looking at it now. I don't actually remember that. So, what other question?
You know the extra credit one on homework 2?
Yeah.
Could you walk us through that if there's time?
I can do it right now. So I need to go look in solutions. So this was the bonus problem. This one, right?
Yeah, I think so.
Okay. So here's the frequency response of the filter, which is given in the problem statement as an ideal low-pass filter with cutoff frequency at pi/2. And you're given an impulse goes into this. So this W of n is going to be the impulse response. And impulse response to the filter, which means it's the inverse Fourier transform of the frequency response. So now I write out what is y of n going to be. Y of n is going to be w of n, and then it's w of n times minus 1 to the n, which is the same as cosine of pi n, which is also the same as e to the minus j pi n, or plus j pi n. It would be the same difference. So now we look at that down here in the frequency domain and say, okay, that's going to be the frequency response, or w of e to the j omega, and then from the frequency translation theorem, w of n times e to the minus j pi n is going to shift that spectrum by pi. And then I just drew these two pictures in here to say that, okay, one gets shifted and the other one doesn't, and then when they're superimposed on each other to within points, I guess, you know, I just say it's 1 at that point. And when I say points, I mean are we quibbling about where does it go from 1 to 0? It's like in the frequency domain, because it's continuous, it can go down to touch pretty much. I mean, that's the simple idealized thing. Obviously, if you were building this in practice, you would have to have some overlap in there. You'd probably end up, if there was a reason to build something like this filter might have a little bit of overlap, so it might do something like that, so that on the translated one over here, it does that. So when they superimpose, then it fills that in. There's actually a type of filter that is in this problem set number 4. It's called it's not a quadrature mirror filter bank, but it's a similar type topology where you have this sort of thing going on. And they do this in coding theory right now. Speech and audio coding uses it too, where you will take subband coding, and the idea of subband coding is to try to save on the number of bits that have to be sent through the internet or into your home. So they will subband code the individual subbands with different numbers of bits to protect them from errors in the transmission, but they can get a net savings in the bit rate. I think it's called perceptive coding, where you maybe give less bits to the bands of frequencies that don't contain nearly as much valuable information for your perceiving, you know, the sound quality, and more bits where you need it. And those ideas are used in speech vocoders in cellular telephony too, most certainly. I mean, the bits are giving you the quality where you need it and the quality where you don't need it. And I think you've maybe witnessed that before. What happens if you take, and you're talking on a phone and you're really close to some music or something and you're listening to it through the cell phone? Doesn't it sound usually kind of wonky? It's because of the perceptual coding that goes on there. And that makes sense, right?
And with this problem, I guess the most confusing thing to me is on the diagram, it's in time domain, discrete time domain, and in frequency domain, like H.
Oh, over here?
Yeah, why is it shown in frequency time?
Well, this is kind of tradition right here, that in a block, you can put anything you want to in here. You could say it's h of z, you could say it's h of n, you could say it's h of e to the j omega. You just understand that those three are related through transforms, right? But the diagram's being worked in the time domain. It's just the representation here was it's the frequency response. It might be, like in this exam tonight, it might be h of z for the z transform problem or whatever. And I think I already told you that in chapter 5, is it 5? Yeah, Chapter 5 is all mixed together. It's really everything taking, you can start using everything all at once, and then properties and things, so that kind of thing happens. It's supposed to make life easier, not harder, so. Any other questions?
Can we go to question 4 on the phone like that?
Sure, it's still open here. I turn this off so I don't draw on the pages. This one, right?
Yes.
Okay.
I guess I'm just not sure where the D omega, like the second line, I don't know where it's coming from.
Okay. So in this particular problem, I think the way I worked it was I said, okay, I'm going to start on the left-hand or the right-hand side in the frequency domain. So I'm going to create at this point j times d omega of x of e to the j omega. So I'm going to take that, and I'm going to now plug that into the definition of the Fourier transform. So I'm going to plug in the forward transform wrapped around over here. So this is the forward transform right in. It's probably not going to work that well. So there's the forward transform, except I've already taken one step on it. I already took the differentiation operator and moved it inside. So this is the forward transform of x of n. And I want to then establish that this is going to lead to this thing on the left side over here, and I will have started from n x of n. So in my approach, and this wasn't the only way you could work it, but this is the way that seemed easy for me to visualize. So I take that derivative operator inside the sum, differentiate term by term, and that's from linearity, and then I operate onto that product, and the only omega term inside of here is, pick a better color. That's the only thing that the d omega finds to do anything with, so it operates on that and pulls out minus jn. And then I can rearrange it, because the minus j that came out goes with this plus j to become a plus 1. And then I'm left with n times x of n. So since we started over here on the left in the red box, and we end up with something that appears to be the Fourier transform of n times x of n, that establishes the proof. But you can start on the other side if you want to. And probably when I graded this last year, I probably had people that were starting on one side and then jumping to the other side. And the thing that I don't want you to do on tonight's exam, and I don't remember what the problem is exactly, there's something kind of like this though. Don't, change what you're doing in the middle of it without letting me know, because I end up looking at the paper and I end up seeing a hodgepodge of stuff and I don't know what you're doing anymore. If you really scribble your paper up, just flip it over and write it out again, and then just maybe X out the one that you don't want me to look at for starters. I will look at stuff if I see something X'd out and then I see something that you tried to do and it looks even worse than what you X'd out, I will try to grade the X'd out part. Does that sound fair?
That sounds fair.
I'm just looking for something that looks like you had your brain going properly. Okay, other questions? Okay, now we're going to go detour into where we were. We're going to jump back and take a look at this idea, but before we do that, I'm going to do some things in the Jupyter notebook that I already had put out there. So I did repost the Jupyter notebook yesterday, I think it was. Wrong button. So this is for Chapter 4, and let's see, is this running? So preamble is in here of what we need to load up. Just writing down some things about the low-pass sampling theorem. And there is a function in the SIG-SYS module that finds the principal alias value. Oops. I wasn't sure whether this had run or not because my computer rebooted between the time of leaving home and coming over here. So start over. Okay. So this is mathematically what that does, but for me, when you're working a homework problem or when I'm messing around, I sometimes like to know. So the first argument is the frequency, and that's the sampling rate. So I can look at principal values. As a matter of fact, if I do this as a sweep, I can sweep from 0 to, let's see, I don't use linspace that often, so I have to remember how does linspace work again. You have the start frequency and the stop frequency and the number of points to put in there. So I decided to use linspace, go from 0 to 100 and a total of 200 points. And then I'm going to map it through the principal alias function. So it's going to produce this for its output. So as the input sweeps up, if I'm sampling, in this case, at 44.1 kilohertz, I know 22.05 is my folding frequency. And as soon as my input goes above 22.05, it folds around and it comes out at this frequency. And so this just keeps zigzagging back and forth. And the way you read the chart is you say, if my input signal is somewhere between 40 and 60, then it's reflecting at the output into a band from 0 to 5 as an alias frequency. Does that make sense? Just to understand how the aliasing would occur. Normally we protect an input from aliasing with an anti-aliasing filter, but this is just part of what you do in the first few homework problems, which you're going to be tuning into right after you're done with the exam. So this function can be helpful. It just helps visualize what's going on. So I picked an example here. I said, suppose I have sampling rate of 20 kilohertz and I put in input frequencies in cosine waves at 2 kilohertz, 18 kilohertz, and 22 kilohertz. So what my mind would do, sampling rate is 20 kilohertz. To avoid aliasing, I have to keep the input less than 1/2 the sampling rate, right? So 10 kilohertz. So the 2 kilohertz will come out properly. The 18 kilohertz is going to get aliased, and it's 2 kilohertz below 20 kilohertz. So sure enough, when I run principal alias here on it, the second value of 18 comes out at 2, and 22 goes in at 2 kilohertz above the sampling rate, so it definitely is aliased. They're all aliased to the same frequency. And just to kind of prove that that's also true, I went down here and I just plotted all three of those frequencies with the sampling rate being 20 kilohertz. And they all three come out the same. Now, they're not the exact same waveform, but they are the exact same period, same frequency sinusoid. So what is going on here? The one at 2 and the one at 18 comes out inverted with respect to each other, and the one at 22 does not. So what's the explanation for why the one at 18 is coming out flipped over? Cosine's an even function, sine is an odd function, right? So what is the frequency that's really going in up here from the math in terms of the alias frequency? It's really a negative. 18 is getting aliased relative to 20 kilohertz, so it's actually minus 2 kilohertz is what the frequency would be. So it folds around like that, and you can see that from a picture like this. This is actually getting it on the opposite side, so it's getting to a negative value. And if you wanted to prove that to yourself, if I replace these guys with cosines, and ran it again, now it looks all the same because that's an even function, so it doesn't get inverted because of a negative frequency in this case. Sound good? I mean, it's negative modulo 2 pi is what it comes down to. You find the closest value of 2 pi to that frequency, and if it's sitting 2 kilohertz below, like it is in this case, that looks like a negative frequency. Another query is, and I did not assign a problem like this time, but it will come up in another example, is the idea of sampling bandpass signals. We looked at that in that example with the GUI slider stuff that I was doing, where we could see if we undersampled the bandpass signal, we could get by at less than the Nyquist rate. So I have some text in here just explaining what's going on with bandpass signals, but actually I'm just going to go back over to, and remember I'm on page 14, and I'm going to jump way up to an example that we'll eventually go through. We'll eventually go through this example, which is just my own creation. It's not in the book. It's digital radio receiver techniques. This is a cellular telephony example. But in this idea, or this example, I talk about bandpass sampling, or IF sampling, actually. And the equation in the blue box right here is the one that tells you how you can find the sampling rate. So the sampling rate, if it satisfies, in this case we're trying to make it satisfy fs over 4, but it has to do with finding what bandwidth B, knowing the bandwidth B of the signal and then figuring out what the sampling rate needs to be, not the total bandwidth, but the bandpass bandwidth. So I worked for the founder of Navsys. Has anybody ever heard of Navsys? They do GPS stuff. They're up there on Baptist Road on the west side of the interstate. I'm pretty sure she still has her company there, but she's, I don't know, she's not a young person any means whatsoever. You can't see that building anymore because all those warehouses have popped up. Visualize what I'm talking about. It doesn't really matter, but I worked for her for a while on GPS stuff, and she always said, bandpass sampling, I just have to sample at twice the bandwidth. She just said that's all it is, and I said, well, it's not necessarily true, you can't do that, but she was the owner of the company, PhD in mechanical engineering, and she had to be right. I mean, I wasn't going to argue with her about it, but I just said to myself, well, it's not exact. If we were to go back and look at some materials that I have from Tom 1, because sampling theory does show up in there, this is a theorem that tells you exactly how you have to set the sampling rate relative to the upper frequency of the signal, and then W is the bandwidth, and then you're allowed to find the sampling rate based on this formula right here, where M is the greatest integer, less than FU over W. I'm going to run my Python code, and we're going to try this equation out, see if it works, okay? It's not a big deal in this class, but it is something that shows up in software-defined radio, and if you end up working in a company where they have IF sampling or undersampling like this, you'll look at it, and I don't want you to go away from this class saying it's always got to be greater than twice the highest frequency, and if you're not doing that, it can't work. I want you to just accept the fact that yes, it can work, and it's done frequently. So I wrote a little helper function here, and this was kind of like similar in idea to what I described last week, saying I would write a helper function to help you draw pictures for the homework. I haven't actually done that yet, but maybe I'll work on that while you're doing the exam. But it's similar in idea to this. It's not exactly this thing, but this is a function that allows you to plot spectral translates and show what goes on if you're not sampling at a high enough rate. And it's designed for bandpass spectra. So you get to put into it a range of frequency values that you want to plot over in your plot, sampling rate, and then how many translates you want to show up and down the axes to make sure that something falls into place in the band you're looking in. And then you get to specify the bandwidth of the signal as a range from, in this case, 2 to 3, but it can be any number. It's just what I say in here. So I've already compiled this. There's a couple other supporting functions that are used in here, a triangle shape and positive and negative. I don't even remember why I have that in there, but it's in there for a reason, obviously. So let's take an example. Let's run from minus 20 to 20 hertz, we could say, kilohertz, whatever, step in 0.01 units. And now we're going to create the bandpass spectrum over that range of frequencies, and I'm going to set the sampling rate at 20. I'm specifying 8 translates, and I'll try to show you what that means here in a second. And then I'm saying the signal bandwidth runs from 8 to 10. So based on what I've told you so far, if the signal goes from 8 to 10 and I'm sampling at 20, I'm satisfying which sampling theorem? The low-pass sampling theorem or something I was calling the bandpass a few minutes ago. Yeah, it'd be the low-pass. So let's just see if that draws correctly. And I use different colors. So red is the original and blue is the translate. So that looks good. Now I'm tempted to flip back over to this. So we know our signal has a bandwidth of 2 hertz, right? Because it goes from 8 to 10. Let's go back and look at this theorem over here. I'm almost tempted to draw on the whiteboard, but I'll stay on here for now. So in this case, W, just following what I have written down here at least, and the upper frequency is 10. So M is equal to 10 over 2. Greatest integer less than or equal to 10 over 2 is 5, right? 10 over 2 is 5, and that's the greatest integer, so that's 5. So that says I should be able to get away with Fs equaling 2 times 10 over 5. My writing's not that bad. My tablet's working poorly. That's why that 5 looks very distorted, but 4 should work. Following what I'm doing, so I should be able to sample at much less than 20 because this says I can do that. So let's just try that over here in Python. I have this was set up already, but okay, same problem. So I'm going to set the sampling rate at 4 and then have it draw the picture. There it is. It's right there. But I wouldn't really be fond of using this because this equation just showed me what can work, but this is packed, right, edge to edge. So I really need to have some sort of a guard band in there if I wanted to have a realizable filter work with this. So it's better to either pad in advance by, defining it to be something else, or what I did after I did this, I said, let's see what 5 does. So there's a little bit more space in there now, and then if I was to go to 5.1, which I think I did down here. This is better still because now there's a little bit of a pad everywhere. There's a little gap in here and in here, so you could mess around with it depending upon the design of the filters and everything. Usually when I've had to do this, I've had to just play around with things depending upon the shape of the filter. I had a project I worked on for a company in California about 2 years ago that was doing something for cellular 5G for a standard called ORAN, Open Radio Access Network, and that's something new in the technology field for cellular. It used to be that the vendors were specific to the standard and you couldn't mix and match. Certain vendors were the only ones you could buy things from, but now with the new 5G, newer standard, ORAN allows anybody to make a cellular base station as long as they conform to the standards document. And this guy, he was a microwave engineer, and he wanted to have a bunch of FPGA developers and other electronics type build an ORAN base station for some investor. The project failed after a while. The investor lost confidence and they canceled everything. Most of us got paid for the work we did do, but I got involved with doing some undersampling analysis with a microwave filter designer who had designed a particular microwave bandpass filter, and I wanted to just see how it would protect the ORAN band of interest and then also reject adjacent signals from getting into the front end of the receiver. It was kind of a fun project. I got to mix DSP, some sort of plotting techniques like this, along with S parameters for the microwave filter that I worked with. And I've certainly done that before too. Kind of cool. So you can mess around with this, obviously, if you want to. Like if I was to say, well, I'm willing to sample. Well, let's just, I said I would show you what happens if I don't put enough translates in. Suppose I only put in 2. It's kind of like void. I didn't get all those periodic, extensions or whatever. So you've got to be really careful when you're using this that you put in enough translates. So 4. It's still lacking, right? It doesn't have enough. I'm looking from minus to plus 20. I should see the same thing everywhere because everything's supposed to be periodic. So I just put in 8, and that showed what I was hoping to see. I guess the whole reason why you would not use way more than needed is the graphics redraw time. Why make a plot where you're drawing all these things that are not seen because they're outside the view of the window? The computer is cycling through that, but it's not showing any of that. So that's what it came down to. That would be an innovation to add to the software, figure that out. Any questions on that? Okay. This is a good example, though, of things that I've had to do for projects I've worked on for people. It's like I have to see what I'm doing. I have to draw pictures, and I have to basically write Python code to draw pictures. And if you're going to write some code to draw pictures or write code to do anything that's sort of, moving outside the box, what do you have to do for sure? You have to have a simple analysis model for something to say, I know if I do this from a simple analysis and this, I should get this. So you have to have some sort of a test bench to test your code with. Does it work properly for this simple case? And then you can gain more confidence that it's hopefully working for the more exotic real case. At least that's been my way of doing things. And if you get involved with working for software, development team like I have on more than one occasion, where I may be the only electrical engineer, there's computer engineers, and then there's computer scientists. They talk about testability and all of the proper methods, the agile methods for, having means of testing and validating your code. And of course, I don't make that a practice of me too much, but I have had to do a little bit of it, and I took some classes at the Scientific Python Conference on how do you write essentially testers for your code. Like Scikit DSP.com has got a library that my co-developer, Trant, has created that before he does a new release after making some changes, he runs the whole suite of tests on it to see that it comes up, and a test just gives you an okay or a good. So you have everything distilled down to a simple pass, 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 maybe one fail, and then you go drill into that. Just like where I've been working, and I'm not working this week. I finished that project, so I'm not working at all until they give me something more. But they've been doing all that testing of building the FPGA and verifying and testing everything to make sure that it builds properly. Speaking of Scikit DSP.com, a new release for it did come out. Charanth put forward the one for the Z-plane. He had another couple that he had bumped into, so that's why I put that posting up on Sunday. It's very easy to install it and just get the new version on your system now. Okay, we'll get back to this half-sample delay. Nobody's going to take Comm Systems 1 in the spring, right? Because you're graduating? There's a possibility I might teach it, at least start teaching it, and then hand it off to somebody. I don't know. Maybe. All the materials are on the website right now, so. The only reason why I said that is because Dr. Trimboli was asking me about it a couple of weeks ago. And I said, I'm going to be on a Viking cruise on the Rhine River in late April before the semester ends. I said, no, I'm not going to stay here to finish class because I've already paid my money and that's a done deal. He said, oh, we could arrange for that, so.
Is he not going to teach it anymore?
Well, the guy that taught it, Mark Frank, has taught it the last few years, but I don't know. I don't know what's going on with him. I had heard that he was going to teach this class, and then he dropped out at the last minute, and I'd heard that some other things had happened, but I don't know anything official about it. Okay, so we want to back up to now is this really big topic, which also leads into a homework problem, or 2, or 3, and it just starts showing up. I want to go back over here to this idea of discrete time processing and continuous time signals. This is exactly the type of thing that's done in 4680, which, John, you've been working with that board. This is exactly what you get to do. You hook it up with analog test equipment around it. You put some digital filter or some algorithm in the middle of it, and then you characterize it. So how does that work out mathematically? That's what this section is all about. So it says our input is X of n is a sampled analog signal. It goes through a continuous to discrete converter. We know that the spectrum of the input becomes the spectrum of X of n, which is X of e to the j omega, with all the translates of that spectrum showing up here, and then the 1 over t scaling factor from the sampling rate clock. And then making a jump to the tail end, we know that whatever comes out of the filter y of n gets interpolated with a sinc function to become an analog signal, y sub r, for reconstructed. So if we put that in the frequency domain for the output, that's just going to be the reconstruction filter times the output spectrum of y of n, and just write it out as a piecewise function saying it's going to be 0 otherwise, and this t is in here because remember that's the gain of the reconstruction filter. Remember that from last week. To go further now, we have to make some assumptions. So now we take the leap forward to say if we want to relate the input to the output in the continuous time domain, we have to know how x of n and y of n are related. So we know for LTI systems, the spectrum y is frequency response of h times x of e to the j omega, and we can plug that in now as h of e to the j cap omega times t, because that is just, remember that is just little omega. So that's nice and easy, and then we can take the x of e to the j cap omega times t and write that as all of the images of the original input spectrum. But then if you make the assumption we either have an anti-aliasing filter or the input is just plain band limited so that it doesn't have any spectrum above the folding frequency, and the reconstruction filter is ideal, then we get that the spectrum at the output is just frequency response of the filter with a variable change, the spectrum of the input signal from the analog domain. Or we can define an equivalent response being the spectrum or the frequency response of the digital filter if we're within plus and minus fs over 2 or plus and minus pi over t in the omega domain. So it made the assumption that the system is LTI and that the input signal is band limited, which is generally the case. It's certainly very much the case in the 4680 lab. You've already characterized the audio codec, I think, right? It runs very close to the folding frequency and then it just drops very, very rapidly. It crosses over a tiny little bit. And I think there was an experiment you did where you listened and you could hear it actually cross the folding frequency and have a slight dip in pitch, and then all of a sudden the amplitude, it's gone. I don't know if that...
I think that might be the line I'm on right now.
Okay, okay. There's a very high order digital filter because it's an oversampled A to D converter, which we'll be talking about, and it'll become clear how that can be done. It's really very, very nice stuff, I think, the way this all works with today's technology. So here's a little example of putting this into practice. Just for simplicity, say we have an ideal low-pass filter that cuts off at little omega c, and then we're going to assume that we have the analog signal that comes in has a spectrum that's band limited above the Nyquist rate. It goes out to omega c also. So nothing is going to happen that's going to surprise us in any way. The input cuts off at omega c over t, and the low-pass filter cuts off at omega c over t. But if we should make omega c less than the spectrum of the input, then we're actually going to be modifying that triangular spectrum to make it look like a house, is what I like to call that. And then the reconstruction filter comes along, and then we get a slightly band-limited version of the input. I think I got some of the terminology I had written down up here confused. But the input spectrum, it cuts off at omega n. was that? Oh, I got a voicemail, so my watch says. Okay, so this is an ideal low-pass filter, and we can turn it into a variable cutoff frequency if we vary the sampling rate, which is kind of a bizarre application, but by doing that, what we'll be able to do then is make it look like the digital filter's bandwidth is getting wider relative to the underlying sampling rate, and it will either take away more of the input signal or leave more of it present. And it also has an advantage that because it is an ideal low-pass filter, it says that the sampling theorem is easier to satisfy. Rather than being omega n less than omega s over 2, it just has to be less than omega c over 2, or little omega c over t. So it's just kind of an interesting twist on things. Here's perhaps one of the last things I'll do for tonight is just an example of how we could follow all the things all the way through, from an analog signal all the way through the digital and then back out again. So here we have a digital filter that has this amplitude response. It has a pass band, it rolls down into a stop band, and then of course it repeats again relative to h of e to the j omega, since it's a digital filter. And then I'm going to mark some things on these axes because I'm going to assume that the input signal is composed of 3 sinusoids, 1 hertz, 6 hertz, and 4 hertz, and the sampling rate is 5 samples per second. So F1, the 1 hertz signal, is sitting right here at 0.4 pi. F3, the 4 hertz signal, is sitting right up here at 1.6 pi. And then F2, the 6 hertz signal, is sitting at 2.4 pi. All of those are identical, kind of like the example we looked at earlier, where they all alias down to the same frequency. Magnitude is even function of frequency, phase is an odd function. So what's going to happen is the signals that alias will get different phase shifts. The one that's properly sampled at 1 hertz picks up an angle of minus phi. The one that's at 4 hertz picks up an angle of plus phi, just because it's negative relative to 2 pi, and then the one at 6 hertz picks up phi also. If you look at in the time domain what the input sampling looks like with the aliasing, this picture just shows you that where the sample values are coming from relative to the underlying input waveform, x1, x2, and x3. 2 of them lie on top of each other, so there's nothing, there's only 2 waveforms actually shown. And then if you were to look at all 3 of these, and this is as if to say you were sitting in the lab and you fed in the 1 hertz signal, it comes back out with an amplitude shift and a phase shift from the filter, and the 4 hertz and the 6 hertz also do. The one that's at 4 hertz, because it's a negative frequency and it's a sinusoid going in, is kind of like the example from before. This one, let's see, gets inverted, or should get inverted. Maybe I got this backwards. 12 hertz, 4, yeah, this is the 4 hertz. This is the one that gets inverted because it's the sine and it's sitting actually 2 hertz below the sampling rate. So if you don't have any protection in front of the A to D, it just lets anything pass, ideally at least, and aliasing, so all of those look very similar to each other. In the lab, this isn't possible to do with our current hardware that we have in the DSP lab, but in the beginning when I was teaching with different hardware, I did have some hardware that didn't have the anti-aliasing filter. Actually, I had an Arduino that I used with an A to D and D to A that did not have either the anti-aliasing filter or the reconstruction filter, but just kind of gives you a flavor for what things are doing. The obvious choice, though, is to don't purposefully let signals in that are above the Nyquist rate. So it behaves the way you'd expect. The digital system on the inside can now be programmed, and you can change algorithms. You could change the shape of the filter, the phase shift, magnitude and phase, and make the behavior be a programmable system rather than electronic components. Maybe before I go on from here, I'll just comment. I'm going to start this example, but then we'll stop before we get back into the Python. What if you're coming from an analog way of thinking, which probably most of you are, because EE's degree is still mostly analog thinking, I think, for a lot of it, especially in the very beginning of what you brought through. You'd say, I like this, I like the programmability, but you've got to put down that A to D converter. You then have to have the computer that can run the algorithms for the filter. Then you have to have the D to A converter, the clock generator, and probably have the anti-aliasing filter in front to protect it from letting signals above the folding frequency in, and then the reconstruction filter. So what do you have? You have some expense involved. You have what I call instantiating stuff that if you're like what Professor T. Camp wants with the capstone project he's mentoring, original analog circuits, simple analog circuits, not integrated circuits. But we've pressed it forward so we can instantiate all these things pretty readily. And all of us have cell phones. We listen to music. We talk to people on our phone. So when we have a platform where stuff is already mostly instantiated, it doesn't really take that much more to do certain other things. Which makes me think of my neighborhood has been torn up for the past month or more by this company called Masada. Has anybody seen a truck around town with a name on it, Masada? They're a contractor, utilities contractor. They are the prime contractor for the city of Colorado Springs build out of a fiber optic network for the entire city. Not MetroNet, not one of the other ones from down south, but our own utility company is doing this for the entire city. In my neighborhood, just basically 2 miles that way, they've been, where I live, tearing things up, doing the lateral boring or drilling, those rigs that you see with the tube that goes down and then it inserts tubes as it's boring. I read about this on the internet because I wanted to understand they could have potentially torn up my front yard, and they tore up my side yard instead, but they didn't tear up the landscaping where it's really pretty expensive stuff, but they're just putting things in. They put a big orange tube in that holds the fiber, and then they put in a lot of utility type fittings. They'll put in what they call vaults. We have vaults already in our neighborhoods that have electrical stuff in them, have cable TV stuff, and now we're adding more vaults for fiber. And then they put in a pedestal at various locations. I've got one of those. I've got a vault too, but I've got a pedestal in the backyard that sits up high, just like the cable TV ones do. That's where they go inside of when they're going to hook somebody up eventually. How long is it going to take? I said, so how long are you going to be doing this? 4 years' time. How many places in the United States have done this? We're one of 2 cities. So I say to myself, why Colorado Springs? Why are we making this huge investment and we all pay our electric bills, gas bills, water? Why did Colorado Springs do this? The guys doing the work, half of them don't speak English, but the ones that I can talk to, because I like talking to people that are doing technology stuff, they don't know why. They just know that they got the contract for 7 years or something. part of their business is in Missouri where they're doing something too. But I say to myself, why did our city decide to do that? I mean, you're young, so you come up in the fiber age, but putting fiber infrastructure into a city is not a trivial matter, right? I figured it would never happen in my lifetime. I just didn't think it would happen. So why Colorado Springs? And are we going to bankrupt ourselves or something? It's something to think about. I mean, it opens up lots of possibilities. The guys doing it said, look at what we can do with all this stuff. And I said, yeah, do we need it though? Can we afford it? Why did 5G not build out very fast? And those of you probably wondered about that like I did. My phone could do 5G, but I didn't have any 5G towers for the longest time in Colorado Springs. It's expensive to put all that infrastructure in, rip out old stuff, put in new stuff. So somebody will answer this question for me someday, somewhere, why we're doing it. But does that make you feel special? You're living in a city that's becoming, you know, fiber optic centric. Pretty amazing. Comcast is who we get our cable service from, and they provide all the services. So is the city of Colorado Springs going to become managed, you know, sell like what Comcast does? I don't know where all of it's going, but they say they need it for communications across the network with all, you know, they have wireless meter reading and other things. They say they want the fiber for doing that, but there's a huge amount of capacity in the fiber. So what we're going to go off and do, we don't have time to do, but this is another spin-off off of this section looking at a type of digital filter design that's called impulse invariant. And you take the same architecture that we were just talking about where you have the C to D and D to C, and then implement a digital filter that is an impulse invariant version of the analog filter. So, and that's in one of your homework problems too. So I will put up the hints in a few days here, or soon I should say. So we sample the impulse response of the analog system, and then that gives us our digital filter's impulse response, and we can relate that back to the Z domain and so on. We'll go through that. A lot of what's in this example is exactly what you do in the homework problem. So don't reinvent the wheel. Make sure you look at this example and understand what's going on. The homework problem's not really crazy hard or anything, but I actually have, I did it in MATLAB originally, and then I redid it in Python, so that's in here too. I actually made a correction to my notes. Page 23, it was MATLAB, but then I changed it to Python, and there's code given, so some of this stuff will also be useful when you work this homework problem. I'll make sure to identify it on the hints page so you know what I'm talking about. Okay, we're at 5:44. I'm going to stop the recording unless anybody's got a last-minute question. Okay. For those of you that are going to watch this video that are not at UCCS, we're having an exam today, so this is today's lecture.